This is the Satellite Foundational course for GOES-R training on the baseline cloud products. My name is Scott Lindstrom, and I'll be describing these products. Mark Cooley from NOAA is the current overseer of them. The subjects of this GOES-R baseline products training are the different cloud products boxed in yellow on this slide. There are a lot of them, and some, chiefly the cloud mask or the clear sky mask, have a big influence on other products. Learning objectives for this training are listed on the left. You'll learn which ABI bands are used for products, how the products are produced, there is a specific order, the temporal and spatial resolution, and some sample uses and limitations. GOES-R baseline products are listed on the right within AWIPS. These products are available in AWIPS under Derived Products in the Satellite menu. You'll note that different products are available under different domains. Note that cloud layers are not discussed in this training, but there is a quick guide for those available at the link. This flowchart shows how the products are computed. The cloud mask is computed first, then cloud type and phase, then cloud top parameters, and then cloud optical properties. If you find something suspicious in a cloud product, or in a product that might rely on cloud clearing, Step 1 should be to examine the cloud mask. If cloud masking is wrong, it can introduce errors into every variable within the dashed red box. Similarly, if cloud typing and phase is wrong, cloud top pressure and microphysical properties will be affected. Each cloud product builds on its predecessor or requires information from the predecessor. Clear sky mask is produced with every image, and a CONUS example is shown here. Clouds are denoted as white. Clear regions have missing values and are transparent. Note that circled region over Virginia in the visible imagery. Clouds are not apparent in the visible, but they are in the 1.38 micrometer cirrus channel. So the clear sky mask correctly identifies the region as cloudy. The clear sky mask is computed for every image. It has 2-kilometer resolution. The default is clear. The algorithm seeks evidence of clouds. It is produced out to a local satellite zenith angle of 70 degrees. There are some known limitations with the cloud mask, chiefly at high viewing angles, over warm clouds, and in coastal regions or near the terminator, the divide between day and night. Which bands are used to create the ABI cloud mask? The visible, 0.64 micrometers, the cirrus channel, 1.4 micrometers, and the ice channel at 1.6 micrometers. The infrared channels used are the 3.9 micrometer channel, the low-level water vapor at 7.3 micrometers, and the 8.4, 11.2, and 12.3 micrometer channels. Cloud mask is computed up to a satellite zenith angle of 70 degrees, which is shown graphically here for the GOES West and GOES East locations. Note that the cloud mask over most of Alaska and the eastern U.S. cannot be quantitatively computed from GOES West. Similarly, cloud mask for much of western Canada cannot be computed from the GOES East position. Some cloud products computed subsequent to cloud mask are not computed all the way to a satellite zenith angle of 70. They cut off at 62 or 65 degrees. Once cloud mask is computed, cloud type, as shown here, is computed. Cloud type is not baseline and is not available in AWIPS, but it is used for other products. Cloud type is a way to identify cloud layers and cloud types. The baseline product associated with cloud type is cloud phase. Cloud phase is produced every 10 minutes for the full disk domain, every 5 minutes for CONUS, and every minute for mesoscale domains. It's computed out to a local zenith angle of 65 degrees and only uses infrared bands to avoid day-night discontinuities that would arise if reflectance bands were used. The baseline cloud phase product is available in AWIPS and includes 4 separate categories: warm liquid water clouds, supercooled liquid water clouds, mixed phase clouds, and ice phase clouds. Here's an example showing visible imagery on the right and the cloud phase product on the left. You might also compare this product to the day-cloud phase distinction, RGB. Cloud top height, a baseline product that is very useful for aviation, is computed for every full disk, conus, and meso image. For full disk and conus domains, the product has a 10-kilometer resolution, meaning a 5 by 5 pixel footprint can be used. The best 2-kilometer pixels within the footprint give the information. In the meso domain, there is a 4-kilometer resolution. That is, a 2 by 2 pixel footprint is used. Height is computed using bands 14, 15, and 16, that is 11, 12, and 13 micrometers, and it requires the cloud mask and cloud phase. It does not necessarily give a good answer with thin cirrus. Thin cirrus is a problem for many cloud products. Cloud top pressure, a baseline product that is also used in aviation, is derived simultaneously with cloud top height and cloud top temperature. It is computed for all full disk, conus, and meso images, and has a 10-kilometer resolution at full disk and conus domains, and a 4-kilometer resolution in meso domains. This is the same temporal cadence and horizontal resolution as cloud top height. Forecast model temperature profiles convert cloud top temperatures computed to a cloud top pressure and a cloud top height. ACHA variables are computed using bands 14, 15, and 16 on ABI, that is 11, 12, and 13 micrometers. Cloud top temperature is also baseline, and it's a product that is used in other products because it generally gives a more accurate value than individual channels. It is computed in concert with cloud top height and cloud top pressure as part of the ABI cloud height algorithm, ACHA. The temporal cadence and horizontal resolutions are shown. Cloud top temperature is not displayed in AWIPS in the conus domain. It's computed like cloud top pressure and cloud top height using the 3 longest wavelength bands on ABI, 14, 15, and 16, that is 11.2, 12.3, and 13.3 micrometers. It also has better resolution at 2 kilometers than both cloud top height and cloud top pressure. Here's a reason why you might want to use the temperature product. Which band would you use for cloud top temperature? There are 4 good window channels on ABI. For the 10.3 and 11.2 micrometers shown, look at the cold cloud top circled in yellow. It's a slightly different temperature in these 2 different channels. If you need a threshold temperature for an algorithm, this can make a difference. Here's an example that shows brightness temperatures for the 4 window channels on GOES 16 for the developing cumulonimbus cloud in the circled region. Brightness temperature values are close, but not exact. If you were to use a threshold of minus 44 Celsius, for example, there are values on either side. Brightness temperatures differ by 2 to 3 Kelvin between the bands, mostly due to the presence of water vapor in the atmosphere. Note that the cleanest window, the 10.3 micrometer, which has the least water vapor absorption, is the warmest as expected. To use the most accurate temperature, though, you would want to use the cloud top temperature baseline product. This is the same scene, but 1 minute later. Cloud temperatures have cooled. Temperatures in the window channel at cloud top differ by about 2 Kelvin. The delta T values, showing cooling, are fairly similar, within 0.4 Kelvin. Cloud optical depth, COD, is a baseline product computed using different algorithms in the day and at night. The daytime algorithm is the only one available in AWIPS. The temporal cadence and horizontal resolution of COD are shown. Note that cloud optical depth is not produced for AWIPS in mesodomains. It is computed up to a satellite zenith angle of 65 degrees using the visible band 2, 0.64 micrometers, and the cloud particle size band 6, 2.25 micrometers. The algorithm also requires cloud mask, cloud phase, and cloud height as inputs. The product is similar to the aerosol optical depth that is computed in the absence of clouds, and it's used to estimate cloud thickness, icing threats, and precipitation. Cloud optical depth at night is infrared only. Horizontal resolution is 4 km for full disk and 2 km for conus, and it's not computed for a satellite zenith angle exceeding 65 degrees. The IR product can be used to estimate cloud thickness and cloud bases. It doesn't have a lot of skill for low clouds. And remember, the nighttime product is not viewable in AWIPS. Only the daytime product is. But you can find the nighttime product online. Cloud particle size considers all pixels identified as a cloud by the cloud mask. Cloud particle size represents the cloud droplet distribution, and it's a baseline product. This daytime-only product is computed for every full disk, conus, and meso image. The full disk product has 4 km resolution, and the conus and meso domains have 2 km resolution. It is computed using the visible channel band 2, 0.64 micrometers, and the cloud particle size channel band 6, around 2.2 micrometers. If you combine cloud particle size with cloud optical depth, you can estimate the cloud mass. Also, large water droplets in boundary layer clouds will likely be precipitating. The infrared product has difficulty detecting large particles and low clouds. So the nighttime product is infrared only, and you can view that online. Let's discuss fog and low stratus. A legacy nighttime method for identifying low clouds involves the brightness temperature difference between the window channel, 10.7 micrometers on legacy GOES or 10.3 micrometers band 13 on GOES R-AVI, and the shortwave infrared channel, 3.9 micrometers. Clouds made of water droplets are not black-body emitters of 3.9 micrometer radiation. Thus, the brightness temperature computed from the radiance sensed by the satellite, a computation that does assume black-body emission, will be colder than reality for 3.9 micrometer radiation. In contrast, clouds made of water droplets are more nearly black-body emitters for wavelengths around 10 or 11 micrometers, so the computed brightness temperatures at those wavelengths are closer to reality. Taking the difference between the two values highlights clouds made up of water droplets, that is stratus. That's shown in this color enhancement, and also in the inset using legacy data that shows a cross-section from fog to cirrus. Computed brightness temperatures between shortwave and longwave wavelengths are different because of emissivity differences. Note in the cross-section that the cirrus temperatures are different as well because of subpixel effects that have been described in other satellite foundational courses for GOES-R. The problem is stratus and fog can look very similar from the top of the cloud deck. It's very hard for the satellite to view the cloud base. Because mid-level stratus aren't an important aviation hazard, not usually, the aviation-focused IFR probability field that you can find in AWIPS under the derived products was developed to screen out regions of mid-level stratus and highlight only regions of fog on the ground. The product is shown here over Texas, the same region that we just saw with the night fog brightness temperature difference. In regions around Dallas, where the brightness temperature difference product on the previous page had a strong signal, IFR probability is low. IFR probability incorporates model output. If the rapid refresh model does not show low-level saturation, then it's unlikely that there is fog present. IFR probability screens out regions of not interesting mid-level stratus and allows a forecaster to direct more focus to a potential transportation hazard. Brightness temperature fields cannot detect low clouds in the presence of cirrus because the emissivity differences of low clouds aren't apparent to the satellite when cirrus clouds block the view. In those cases, an example of which is shown over Louisiana, model data can provide information about low-level saturation even when satellite data are incomplete and alert a forecaster to the potential presence of reduced visibility. There are supplemental links on this page for more in-depth information on these products. This concludes the GOES-R training on cloud products and fog detection. Thanks for your attention.